Pop quiz. A sample's half-life is 2 hours. You start with 80 grams. After 6 hours, how much remains? 10, 20, 40, or 5 grams? Pick your answer. We'll reveal it shortly and explain the reasoning. In this video, you will learn what activity means, why radioactive decay follows first-order kinetics, how half-life relates to the decay constant, and how to solve for time, amount, or K with confidence. To begin, remember that radioactive decay is random for any single nucleus, but in a large sample, the rate is predictable. The rate of change of the number of nuclei is proportional to how many are present. In words, the rate of change of n with respect to time equals minus k times n. That rate, measured as counts per second, is called the activity A, and it also equals k times n. The constant k has units of per time. From there, we can use the integrated first-order law. It gives us the natural log of n over n0 equals negative k times t. This equation lets us connect what remains to time and to the decay constant in one clean relationship. Now define the half-life, the time it takes for the amount to drop to 1/2 its starting value. Setting n equal to n0 over 2 in the decay equation gives t 1/2 equals the natural log of 2 divided by k, which is approximately 0.693 over k. Let's try one numeric example. If k equals 0.125 per hour, the half-life equals 0.693 divided by 0.125, which is about 5.5 hours. With that in mind, it's time to reveal the pop quiz. 6 hours is 3 half-lives. 80 grams falls to 40, then 20, then 10. The correct answer is 10 grams because each half-life halves what is left, not the original amount only once. Before moving on, let's clear up 2 misconceptions. First, after each half-life, half of what remains decays. It is never all gone on a schedule. Second, half-life is a property of the nuclide and conditions. It does not depend on how much you started with. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Next, introduce a handy model. The half-life count. The remaining amount equals n0 times 1/2 to the power n. Here, n is the number of half-lives, which equals time divided by the half-life. For example, suppose you begin with 16 milligrams and the half-life is 5 hours. After 20 hours, that is 4 half-lives. 16 halves to 8, to 4, to 2, to 1 milligram remaining. Now go the other way. If 30% remains and the half-life is 18 days, first find k as 0.693 over 18. Then compute time as negative the natural log of 0.30 divided by k. That comes out to about 31 days. To keep everything connected, remember the 3 views: the differential rate, the integrated law, and the half-life shortcut. You can move between them to match whatever the problem gives you. As you practice, watch out for classic errors. The integrated law uses natural log, not log base 10. Keep units on k, like per hour or per day, and do not round the half-life too early, or errors will compound. Here is a quick recipe to use on any problem. First, list what you know. Second, choose the differential form, the integrated form, or the half-life form. Third, plug in numbers carefully. Fourth, sanity check that the amount decreases and that the timescale matches the half-life. In the end, it's really 3 tools for one idea. The rate law says the decay rate is proportional to what remains. The integrated law links amount and time. The half-life relations give t 1/2 as the natural log of 2 over k, and let you count half-lives with n equals n0 times 1/2 to the n. Use the half-life count to see what is left, and the integrated form to solve for time or k. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.